All right. Good morning. I'm gonna mostly just go through the fall 2020 exam today. So I'm gonna start with this ranking acidity page as a bit of a review for you guys. So looking at some pKa's, I might give you some extra ones just because there's some ones on here we didn't really talk about. So there's kind of a general trend. Oops. Which is that for the most part, well, there's a couple of trends going on here, but the big one is that esters are a lot less acidic than ketones, and then aldehydes are even less acidic than that. So an ester is going to have a pKa at roughly 21 versus a ketone, which is going to be around 19, versus an aldehyde, which is going to be around 17. And then when we do these diketones and diesters, we're going to have the exact same concept happen. So if we have a diester, having two carbonyls that are giving resonance once you take off this proton is going to be pretty favorable. But then when you do take off a proton for one of these, so let's draw just a regular ester here. Not screen this negative charge here can donate to our carbonyl when it's in this form, but there's also another form of this where it looks like this, which is going to be a lot harder for this to do resonance with versus a regular ketone. Once you pull off the proton, this can 100% of the time just do your normal resonance. So these esters are a little bit worse when it comes to acidity because of that. So if you have two esters, you'd have a pK of around 13. If you remove one of them and replace one of them with a ketone, it gets more acidic. It's going to be around 11. And then if you replace both of them, it drops all the way to 9. There was one more that was on here. So carboxylic acid has the word acid in it. It's very acidic. This is pK around 3. Okay, so kind of general trend is that if you're adding in oxygens on the other sides, you're getting less and less acidic. Same thing over here. You go from a ketone to an ester, you're just gradually getting more acidic as you go. So taking a look at some of these options here. No, so there's only ranking on the exam. You're not going to do any sort of naming. I don't think we did any naming for this exam. So we're just doing some sort of acidity ranking system. This is our diester here. This is a carboxylic acid. So pK of around 3. This is a diketone. Going to be in this category over here. So pK of around 9. This looks like a diester, but you have an extra carbon here. So really, if you deprotonate this, it doesn't have any resonance. to this carbonyl, it's only being affected by this one. So it's just a regular ester. And then this has an ester on one side and the ketone on the other. So it's this ketoester, should give us pKa of around 11 here. From this point, you're just putting them in order from lowest to highest. So your lowest number is your most acidic. This would be our most acidic. Next is 9, 11, 13, and 21. So if you know your pKa's, this shouldn't be too bad. You guys should be able to recognize these and go through them. All right, let's do some NMRs. So I'm gonna try to split the screen to give you guys a little bit more time if you want to write that. So for this NMR here, we don't have a lot going on. We have a peak between 9 and 10, which is generally an aldehyde. We have a singlet between 3 and 4, and a doublet between 3 and 4. So a CH3 and a CH2. This should have 0 neighbors. This should have 1 neighbor. This should have so triplets, which should have 2 neighbors. We've got 1, 2, 3 carbons here. We're supposed to have 4. And we also are supposed to have 2 more oxygens than we already have. So 2 oxygens is usually either a carboxylic acid, which gives you a little peak at between 12 and on. So like this one here, or you have an ester, which would give you peaks around 2 and 3 and 3 and 4. We somewhat have that. We have another carbonyl, so we could be pushing something up. So there's a strong chance that we're dealing with an ester here. So if we had an ester, that's got this carbon with no protons on it, so it wouldn't have any signals to it, which would kind of explain why we're missing one. It's also going to give us the 2 extra oxygens we're missing. And it's what we covered for NMR this chapter. Let's examine. So taking a look at it, we have a CH3. That's a singlet. It's in the 3 to 4 range. Generally, that means it should be next to the oxygen, because that would put it in the 3 to 4 range. So if I put that there, my aldehyde is supposed to be next to something with 2 protons, which would be the CH2. I've got 2 openings here that could connect to each other. So putting this H here, CH2 here, can give me a product that makes sense. So I'm next to a carbonyl, which should be between the 2 and 3 range. Next to a carbonyl should be 2 and 3 range. It's going to kind of bump it up to the 3 to 4 range, which is why it's showing up over here. I can talk a little bit about why this is flipped over in a second, but first I'm just going to kind of do some numbering. So if this was A, B, C, A should be our aldehyde, B is our CH3, C, CH2 here. So the question in the first class was, why is it not this, where your carbonyl and your oxygen are flipped over? You still have the right number of carbons, you still have the right number of peaks. The real difference is just going to be where these are located. So this is now in the So this was in the next to an oxygen, it was in the 3 to 4 range. This is just next to a carbonyl, so it would show up between 2 and 3. So that will be off here. This CH2 is next to 2 different carbonyls. So this one would be 2 to 3. This one's going to push it a little further, so this should also be 3 to 4 range. Versus this one, which is attached to both an oxygen and a carbonyl. So the oxygen is the 3 to 4 plus the 2 to 3. So that should put us all the way to 5 to 6 range. But it would look almost identical. So for this to be this structure, this would have to go to here, and this would get shifted back down. So they're very close. It's just really about where those shifts are landing, the peaks. Okay, let's take a look at this next one. So we have a peak that's really far down. It kind of looks like an alcohol. It's between 12 and 14. This gives you our carboxylic acid. We've got a CH2, it's a singlet, no neighbors, CH3, the singlet, it has no neighbors. We've got 1, 2, 3 carbons. We're supposed to have 4. Currently have 2 oxygens. We're supposed to have 3. So our 1 oxygen combination possibilities are an aldehyde, which would give us a peak between 9 and 10. We don't have that. Cross that one out. Ketone, going to give us some peaks around 2 to 3. These are roughly in that range. And it's going to give us a carbon with nothing on it, as well as the oxygen. And ether, whoops, I'm off the screen, is going to not give you an extra carbon, so that doesn't really solve that issue. And same with an alcohol. The alcohol is going to give you a peak that looks like an alcohol, as well as it doesn't give you an extra carbon, so you're not really solving your problem there. So most likely you have a ketone left over. So you can draw that in. Ketones next to it is supposed to be in the 2 to 3 range. We currently have at least 1, so that's CH3 here. And then on the other side, it's a little bit far down. So if it was between these two, this would be 2 to 3, this would be 2 to 3. So combining them together should give you around 3 to 4 range. So we can draw an overall structure that looks like this. And this should account for everything. We have 1, 2, 3, 4 carbons, 1, 2, 3 oxygens. This doesn't have any neighbors because it's next to carbonyls. This doesn't have any neighbors because it's next to carbonyls. This should be in the 2 to 3 range, which it is. This should be 2 to 3 plus 2 to 3, so 3 to 4 range here. We can do some naming or some assigning A, B, C. So A is going to be our carboxylic acid, B is our CH2, C is our CH3, and that'll give us our final product. I'm going to do a little bit of this next page, not all of them, but I'm going to go through some of them. I think I did 1, 2, 3, 4, that's 6 of them. Okay, and you don't have to draw it every step. I'm just going to do it to kind of give you guys a little bit of a review of this. So for this first one, when you have the element and the halide, it's going to attack. You're going to get a very large structure from this one. I'm going to draw it down here. From your initial step, you will add a element to both of these sides here. And then adding in hydrazine is going to remove it to just give you your amines. So your final product should look like the diamine version of your starting material. So both these BRs were replaced with amines here. Bless you. Kick this off and bring this back so I can do a little bit of work on it. So our next one, this was our acid catalyzed brominations, which we haven't talked about in a while. So adding in H3O plus is going to form an enol instead of an enolate. So you can pick up a proton, grab, so this is a small base because it's water. This H here to generate your enol. Nope, that's the wrong thing. That's an enolate. Should have an H on there. From this point, you can come down, pick up a BR. Thank you. We will brominate and lose the H plus. And we can add BR to that. In this case, you're more substitute position. Let's see, which one do I want to do next? I'm gonna do. Oh yeah, I'm gonna do this one here. Okay. Or wait, no, did I do that one last one? No, I did that one. Just kidding. Okay, I'm gonna do the clays in here. So I wrote assume cross coupling is your major product. So for this one here, where we have an aldehyde and a ketone, your aldehyde is a lot more acidic. It has a pK of around 17 versus 19, which we talked about on question 1 here. So this is the one that's much more likely to form an enolate. It's about 100 to 1 because it's 2 to the 10th difference in the pKa here. And then from here, so we said assume cross coupling, which means don't have this attack itself, have it attack the other molecule. So this can come down, attack here. We'll pick up a proton to generate our alcohol. This is done in heat, so we can do our condensation. lets us eliminate this water. To form our double bond. I'll write that one again down here. So yeah, for this one, if I tell you to assume that you're just going to do the cross coupling, don't worry about forming all the products. I just want to see the one where you deprotonate and attack the other molecule. All right, let's do the enamine synthesis. So this is the Stork enamine synthesis here. We are going to start with a ketone and what is a large base. So this is the protonated version of LDA. This is going to originally generate an amine that looks like this, because the base that's in solution is this large amine here. We're going to pull off on less substituted side to generate an amine that looks like this here. We can do an attack on our Michael acceptor. So our electrons can come down. Attack at this position, kick out to our enolate position, and kick our other electrons up. And then in our last step, we're going to form our carbonyl, protonate this position, but also we're adding H0+, so this is going to fall off. And it's going to give us a ketone back plus our Michael addition product. So that was over here. All right, I'm going to do two more of these last two on the bottom of this page. So let's take this Claisen condensation. We're going to do a cyclic Claisen condensation. So NaOMe lets us pull off. It's symmetrical, doesn't matter which proton you pull off, just one of these two alpha protons. To form an enolate. From here, we can cyclize. This is gonna form a 1, 2, 3, 4, 5, 6-membered ring here. And we can kind of use that for everything. So let's start with a 6-bone ring. Number it. Gonna put 1 here. Two and 4 both have methyls on them. 1 is where we attacked from, so that should have my ester on it. And then 6 is what got attacked, so that should have my O- and my OMe on there. From this point, last step is going to kick out that OMe. So this carbonyl is going to reform, kicking out methoxide to give me my cyclic Claisen product. All right, last one is going to be another Claisen cross coupling. Let's see. We're starting with a ketone here, throwing in LDA, which is a large base. Which means we're going to form an enolate in our less substituted position. We throw in a ketone here. It says assume cross coupling, so we're just going to attack this and not attack itself. We can eliminate our OH. To give us our Claisen condensation product. All right, so that is this, what, page 3 here, or problem 3 here. I'm gonna skip problem 4 and go to synthesis problems. So we can do some of these. I have enough time to talk through some mechanisms. So let's take a look at this here. Looking at our starting material to our product, there's really 2 different places our starting material could be. It could either be this ring on the left, or it could be this ring on the right. It's the one on the right, we're gonna have to add a methyl group to it. We're doing some sort of alkylation. We probably want a carbonyl, so we can start by just doing that. Throw in PCC. Gives us something to work with here. Taking a look at what we're trying to do. So I'm going to draw this out twice. If I wanted this ring here to be the one in red, I'm going to have to add to this position, which is going to be a little bit tough, seeing as every reaction we've learned adds to this position here. Versus if we want it to be the one that's in purple, we would need to add a methyl to this alpha and then this large group to your other alpha. And seeing as we don't know any reactions that add to this position, this is most likely not going to be the way that we have to do this. So I'm starting from here. I want to turn this into our product, or this right side of our product here. Adding a methyl first is pretty straightforward. We could throw in NaOH followed by methyl iodide. That gives us the dimethyl version of our product, which we wanted. We can do basically the exact same reaction to add this other half of it. This is now quaternary center, so there's no H to pull off. We're gonna have to pull off on the other side. NaOH. Let's see, it's gonna draw down here. Something like this. We've now got our carbon skeleton. We just got to reduce off this carbonyl here. A couple of ways you can do it. You could do LaH, H2SO4, and then H2. I'm going to do the ring nickel one with less steps. So H plus dithiol followed by ring nickel. Can get you to your final product. All right, looking at this next one, I'm going to kind of go through it backwards. I think that's going to be easier. So looking at my starting material, I got 1, 2, 3, 4, 5, 6 atoms here. I need to make a 6-membered ring with a nitrogen. One option would be to replace the Br with a nitrogen and then try to do some sort of a cyclization like that. If I was doing that, I'd probably want something that looks, I'm gonna draw on this page. And the nitrogen there. Probably want to come from something like this, which would come from a carboxylic acid here. Taking a look at this versus our starting material, that seems kind of manageable. Getting from here to here, and then SOCl2, and it should close itself. So to turn our Br into an amine, either do NH2, or N3, or I'm going to go through the phthalimide pathway. So adding in actually, I want it to just be negative. Negatively charged phthalimide here lets us make a protected amine. If I want to get a carboxylic acid on the end, I'm going to need my oxygen to be on the end. So I would need to do BH3THF in order to get an OH here instead of here. We could oxidize this with chromic acid. This is actually going to serve two purposes. So one of the ways you can remove this phthalimide is with H3O plus. H3O plus is just H2SO4 and water. Generally, that's what you're using when you're using H3O plus. So this will oxidize this to a carboxylic acid, but it's also going to cause this to fall off. Question in the chat. Oh, sorry. If you did it in the exam in 2 steps, that's also fine. You could use the chromic acid and then H3O plus. We're not going to lose points from that, but just to simplify things, I'm going to do it in 1 step. From here, throwing in SOCl2 is going to turn this to an acid chloride. This is going to immediately attack, and you're going to get your final product. So this one was a bit tough to think through, but it's only 4 reactions. Same thing with the top one. 1, 2, 3, 4. Yeah, they're both just 4 reactions to do these. Kind of 5. All right, let's go through some mechanisms. These are particularly long. I'm not going to ask you to do this long of mechanisms, but I'm going to go through them anyways, just kind of give you guys a review on them. I can get rid of this one. Scrap piece of paper. This first one is like 10 or 12 steps. I would only give you that. So there was an issue with people finishing this exam on time last time, so I'm not going to give as long of mechanisms. Oh god, this marker's back. Lots of markers going down today. Okay, so our first step, we're going to pick up NH plus. From this point, water can attack, so we just made water by picking up that H plus. From here, we can grab one of these H's. Our nitrogen can then pick up that H. We're going to make a protonated version of our amide. I'm going to draw the other resonance structure where we kind of flip this over. So put the oxygen on top, but also make a double bond to it. Lose that H plus. Although technically the next step is to gain that H plus, so I'm not even going to bother with that. I'm going to have water coming in attack. I'll do this the short way. I'm just gonna have the amine pick it up. So transferring that proton. Kick out the amine. Lose our last proton. To get our carboxylic acid. How many was this? I kind of skipped a little bit. 2, 3, 4, 5, 6, 7, 8, 9, 10. So yeah, this is a 10-step one. I would only give you guys probably a 5. I'd make you like going from the amide to the carboxylic acid kind of a thing, but not have you do both of them because no one had enough time for that last semester. But as a review, a lot of these steps are kind of repetitive and you use them in a lot of these mechanisms. So it's good to go over them. All right, I'm going to do this, which is also a really long one. Robinson annulation. And then if you guys have any other questions, I can go talk about them. So let's draw this over here. We've got diketone growing in NaOH. Oh, this last semester, for whatever reason, we wrote these out differently. So you're used to seeing it as NaOH followed by your Michael acceptor. Followed by NaOH and heat. Technically, you could just throw them all in together. For your guys' exam, I'm going to write them like this because that's what you're used to seeing. So our first step, we're going to pull off an H. Do an attack on our Michael acceptor. This cyclohexane ring is just extra carbons you shouldn't care about. So we're still doing our normal mechanism here. From this point, we can reprotonate because we made water in the first step. And that is the end of our Michael addition. From here, we can do our aldol condensation. So picking up an H. We're going to pick it up here so we can form a 1, 2, 3, 4, 5, 6 membered ring like this Robinson annulation always does. So last step we made OH here. Our negative charge can attack this ketone will pick up an H from the water we just made. This is going to look a lot like our final product, just with an alcohol still. And then from here, pulling off an H. Lets us do the Claisen condensation, forming our double bond. To give you your final product from this reaction. So this would be your aldol condensation. Oh God, I got space. And like the last one, this is a bit longer than something I would ask you guys. This is what, 1, 2, 3, 4, 5, 6, 7. So for time restraints, I'd either ask you probably unlikely addition or aldol. I'm not gonna ask you both, kind of a thing. Not necessarily gonna ask those questions, but to give you a sense of the length of the mechanisms. Okay, so that's all I have for you guys. Your exam is on Wednesday. On Friday, we'll do this all over again with the final exam from last semester. So I will see you guys then.